Well, we are ready to start the experiment with our application. So, first of all, let's access the application. Okay, first action is to create a new workspace that we call PhotoZeta, that at the beginning is obviously empty. So far, let's take the data file we want to use for the experiment. In the specific case, the original photometric training data can be uploaded from the DAMEWARE intro web page. There is the section, test resources in the index on the left. Here there are several samples to be used for experiments. Let's take our files. In order to do this, we have to select the option Upload from URI by copying the URI of files into the Upload tab field. Remember to select proper file type, in this case a simple ASCII file, and go. After some seconds, the pop-up window will notify the successful upload action. Then come back to the Workspace tab and repeat the same upload procedure to get other files for the experiment. The two files have already been created offline from the original dataset file, that is the dataset training.dat. In the page there is explained some information about the files. In this case, these two files are respectively containing the randomly shuffled 80% and 20% of the samples contained into the original dataset file. Just to have a look at the contents of such file, click on the Edit button, and the Feature Selection option gives back the information, the metadata information about the columns contained into the file. And there are basically 4 input columns that are the colors specified as the input samples, and the last one, that is the target column with the spectroscopic redshifts. Now we are ready to start the first experiment, the training of the network. So we create a new experiment into the available workspace by naming it, for example, as train, and in the train experiment tab we have to select the coupled functionality model according to the desired use case of the current experiment we are going to do. In this case, we want to perform the regression with the MLP trained by the Back Propagation. Just a note that this kind of model is simply named as MLP because Back Propagation is the standard learning you'll use it for it. In the other case, we have put the name also of the learning unit, specific learning unit that we use for the MLP. In this case, it is a simple MLP. Well, after selection we have to perform the setup of the model. So we have to specify the use case. In this case we said we want to perform a train phase, and now we have to perform the setup of the model by specifying first of all the input file, that is the train with the 80% of samples, and the topology of the network, for instance the number of input nodes that is equal to the 4 columns contained into the file, the one output that is the spectroscopic target, and we will use the classical empirical rule to select the number of hidden nodes of the hidden layer, that is basically is 2n plus 1, where n is the number of input nodes. In this case is 9. Then other parameters can be left with the default values, but if you want to know about these parameters, you can press the help button, redirecting you in a web page where it is possible to have all information about all the possible parameters that you can set up. In particular, there is also reported the default value for the parameters. In this case, the parameters that we left empty are the number of iterations for the training, that is 1000, the error tolerance, that is the second stopping criteria, where the default value is 0.001, and the training mode, that is basically it gives the possibility to choose the error of the training, that is the classical mean square error plus batch mode for the training phase. So going back to the setup tab, after filling all parameters, we can launch this experiment. Wait for a while. That it depends both on the dimension of the input file and model parameters. The experiment tab reports status of the process. When it is ended, it is possible to look at the resulting information. In particular, there is also the status that you can see during the running of the process. At the end, the pop-up window will notify you that the experiment is finished, and if you click on the experiment, it is possible to see the results. Well, the output is different for each kind of model, of course, and also for each kind of internal use case. The output of the training is made by several files, in particular all models, reports, and an XML file containing the complete setup information as specified by user. Then there is also a log file reporting some information about the executed process, and also an image of the scatter plot with learning error trend, and the most important is the trained weights of the hidden nodes. This is the trained network to be used for next experiments with the model. It is also always possible to download all these files on the local hard disk of the user. So, in order to perform the test phase, it is mandatory to move the weight file from the experiment tab to the final manager 1 in order to make it available for next experiments. So let's do it. As you can see, the trained weights file is moved into the file manager. Now it is possible to use as an input file for other experiments. Then we create the new experiment called test. Select as usual the functionality and model. It's always regression MLP. Selection the running mode, in this case test. And well, in this case the setup is more simple than the training one, because it basically requires to only the input file name and the trained weight file name. It is 20% of samples, the trained weights. Start the experiment. It is basically finished in a few seconds. Go back to Resource Manager and let's have a look at the contents of the results. The output consists basically in the test phase of the same XML and log files, and there is also the output file that is basically the input file with another column added at the end that is basically the output column of the network, and there is also the image reporting the final result scatter plot, that it shows basically the distribution of photometric redshifts against the spectroscopy ones. Well, of course it could be very interesting to repeat the same experiment by also changing the hidden node number in order to see how it changed the results in terms of different distribution. Okay, thanks very much and goodbye.